Hi, this is Mark Weitzman, and I wanted to start a new lesson, sort of an in-between lesson on symmetries. This will be lesson 3.5 on symmetries, gauge invariance, and Yang-Mills non-abelian gauge theory. So it's been a long time since I've used this software or made a video, so I'm practically forgetting how to do it. But just to repeat that, this will be the first video in lesson lesson 3.5 on symmetries. And we'll start with this video on Noether's theorem. Emmy Noether was a mathematician, and she's very famous, and she did a lot of work, but this theorem seems kind of like trivial, but you have to remember this wasn't known back when she discovered it. There wasn't any formal way to do it. And basically, almost all quantum field theory books cover advanced mechanics and advanced electromagnetism, as well as field theory books cover Noether's theorem. And so just for references, there's Borkin and Drell, which is section 11.4. There's Peskin and Schroeder. They do it on page 17. And it's in section 2.2. And there's also a little bit more on it on 308-310, section 9.6. Janicki himself does it later in the book. He treats the quantum aspects. So he does it in section 22, pages 132 up to 139. Then there's Ryder. He does it in section 3.2, pages 81 to 91. Z, section 1.10, pages 76 to 80. Ramon, section 1.5, pages 25 to 28. Hatfield, pages 22 to 24. And Weinberg, section 7.3, pages 307-313. But I'm going to follow mostly Coleman's book. He does it in lectures 5 and 6. Now in 5, he does space-time symmetries. And in 6, he does internal symmetries. I'm mostly interested in internal symmetries, but this first video at 2 will cover space-time symmetries. And for the most part, I'm only going to treat the classical theory right now. Not worry about any problems with normal ordering and some other things. And so what does Noether's theorem say? Basically, it states that for every continuous symmetry, there is a conserved current. And an associated global constant charge. Okay. Now the key thing to realize here is that I said to have a continuous symmetry. There are discrete symmetries, and these lead to things like parity and other possible internal symmetries that might be conserved. But Noether's theorem really applies only to continuous symmetries. So that's what we'll treat. I want to start by treating classical mechanics. Most of this, I'm sure, is already quite familiar to all of you, but review never helps. So let's say we have a continuous symmetry transformation where the coordinates A will always be a label has nothing to do with an index. It's not a space-time index. It's just a field index. So we might have two fields, phi1, phi2. We might have n fields, phi1 all the way up to phi n. So in general, I'm treating more than one field or coordinate, in this case, in the whole lecture. So if we make a symmetry transformation with a parameter lambda, this parameter could designate a rotation, a translation, So we have the infinitesimal version a word I'm sure I've misspelled. So here we have QA goes to QA plus something we'll call DQA. Coleman has his own idiosyncratic notation in this lecture, but it should be easy for you to follow, and it's not standard by any means. So this is sort of like an infinitesimal transformation because lambda, we're using d lambda. And then we define from this, if we have something like this, dqa is just defined as the partial of qa from this above with respect to lambda, evaluated at lambda equals 0. This is just to keep our notation straight. So now the Lagrangian L transforms as dl. It's the partial of L with respect to QA dqa plus the partial of L with respect to Q dot A dq dot A. I guess we're assuming no time dependence here, no explicit time dependence here. Or maybe we're not. We're just finding the change in the Lagrangian under this symmetry transformation. So the Lagrangian may have time dependence, but it won't change that under the symmetry. Unless the QA's, the coordinates, the time itself changes. Okay. And this is equal to, this is also equal to the partial of L with respect to QA dQA plus PA dQA. This is what's a little confusing, dt. So this PA, as we know, is defined by the derivative of Lagrangian with respect to that coordinate. And also, as usual, we always have things like dq dot A is equal to dqa dot. So these commute there. Okay, and I'm going to put a box around this. We're going to use this equation a lot. Now, we define, or Coleman defines, a symmetry transformation as one where the change in the Lagrangian from the symmetry transformation is equal to df dt. I'll talk about f in a second. The key thing here is that this holds for arbitrary transformations, not just functions that solve the equations of motion. So, for instance, let's say we have a Lagrangian that's translation invariant. So we can, whenever we make a symmetry that's translation invariant, the Lagrangian won't change, even for things that aren't solutions of the equations of motion. If we just translate them, they'll also, for the same reason they didn't satisfy the equations of motion before, they won't satisfy it after. Or if they satisfied them before, they'll satisfy them after. And as you may remember from classical mechanics, and as I'll review in a second, as long as the change in the Lagrangian is a complete derivative, that won't affect the action principle. Because we have S prime, this is after the symmetry transformation, is equal to the integral from T1 to T2, L prime, QA prime, QA dot prime, and T dt which is equal to the integral from T1 to T2 of L of these things plus the partial, not the partial, I'm sorry, plus df dt, because we said that dl, or the change in L, is df dt. So the action would be that L prime would be L plus the change df dt. And now this is going to be equal to the prior action S from there. Then we get plus f of q2 at A, comma q2 at A dot, and T2 minus f of QA, I'm sorry, Q1 A dot T1. And the point is that when we make, when we apply the action, this is a boundary term, boundary terms. When we apply the variations in the action, when we vary coordinates, we require del QA equals 0 at the boundary. So if S is stationary, has no variation, this is just a constant, whatever it is, then S prime will be stationary. So that's why we get this definition of a symmetry transformation. As long as the change in the Lagrangian, it doesn't have to be 0. Many times it is 0. But it doesn't have to be 0. As long as it's a total derivative, we're still okay. Now, to show this, again, know this theorem. Is basically an infinitesimal, in this case, infinitesimal symmetry in L implies a conservation law. And here we'll just explicitly exhibit it and show that it's conserved. So take Q, define Q as PA dQA minus F. Again, this is going to be the shortest proof of anything you've ever seen in physics. Okay, so let's compute the derivative. Now remember the definition of the canonical momentum. It's just the derivative of the Lagrangian with respect to the coordinate. Oh, this comes from, I'm sorry. So we have from the, I hate when that happens. We have from the Euler-Lagrange equations of motion. I'm going to use this symbol for that all the time now. Euler. We have that the partial of L with respect to Q dot A ddt minus the partial of L with respect to QA equals 0. So since this is defined as the partial of L with respect to Q dot A is PA, this is P dot A, so I can substitute the partial of L with respect to QA. So we define a symmetry as being something where the Lagrangian doesn't change regardless of the equations of motion. But then in proving Noether's theorem, we use the equations of motion. So now I have plus PA d dQA dt minus dF dt. And this is equal to dl, because if we go back to our definition of dl, which I calculated above, I boxed that, partial L with respect to QA dQA plus PA dQA dt. So the first two terms here are dl minus dF dt. And this is equal to 0. Because we defined, we said we defined a symmetry by dl equals dF dt. So seems like all we've done is just rename symbols and everything, but Coleman does this, he calls it a turn the crank method. The idea is that if you just clarify the notation and clarify the ideas, you can work with any symmetry transformation, just calculate, and you don't have to think. And we'll be doing that in a while. So that's our proof, at least for mechanics, our elementary proof. Let's give some examples. Let's say we have a Lagrangian that's translationally, it's of this form. It will be translationally and rotationally invariant I'll write down a general Lagrangian that you're all familiar with. So this is the product of the velocities, 1/2 mv squared basically. And then I have plus a potential. This is the kinetic energy, and then I'm going to have a potential energy. Again, it's the general so you can see if we translate it, the potential won't change, and if we translate it by a constant amount, the derivatives will kill that. So so this has a symmetry. We know that the change in coordinates for like a translation. Well, let me start over here. We have like xr, the vector goes to, here r is a coordinate indices, plus lambda times a vector. So we're just translating our coordinates by lambda times a vector e. Then dxr is the partial of xr with respect to lambda. Lambda equals 0. And that's just going to be e. Now, as I said before, just from looking at this Lagrangian, we know, even without calculating, that dl equals 0, which implies that f equals 0. And our conserved charge, if we substitute it into our formula, it's going to be E dot sum over R mr x dot r, which is the same thing, implies that since dq dt equals 0, implies dp dt equals 0. P is just the momentum. And since E has 3 independent directions, we get 3 conservation laws, 3 conserved, I'll put quotes around them, charges, because they're just momentum in this case, components of momentum. Okay. Our second example, let's do the same thing. Let's do it for same Lagrangian. Let's do it for rotations. So xr goes to some rotation, which depends on an axis e and an angle lambda. And if we wanted to do the infinitesimal version, we calculate dxr respect to lambda, evaluated at lambda equals 0. And this is well known to be E cross xr. So if you're rotating something, you know, if you're rotating something around an axis E by an angle lambda, and you take the vector of E cross the displacement, that gives you the change in the vectors. So it's like we have, let's do it in the plane. So let's imagine E comes outside of the plane. So this is x, y. E comes outside of the plane, and if we go from like x over here, and we go to x over here, we just have to take our vector out of the plane, cross the position, and that gives the infinitesimal rotation. Okay, I'm sure you all know this. It's very simple classical mechanics. So again, we know that just by looking at that Lagrangian, we know that dl equals 0 and f equals 0. And then q is equal to, again, plugging into our basic formula, PR E cross XR now, because that's what our dxr is, E cross XR. And we can rewrite this using a vector identity. It's just going to be E dot, the sum over R of XR cross PR. Or this is going to be like E dot J. So J is angular momentum. And each of 3 components are conserved. Okay, so let's extend to field theory. Now in field theory, all that happens is that QA goes to phi A of X. X is a 4-dimensional space-time index. And the difference in field theory is that because we work with Lagrangians and we integrate local fields, we get what's called local charge conservation. So this is due to local nature of Lagrangian, which is, the integral of Lagrangian density. We'll call the Lagrangian density Lagrangian from now on. So the difference is that now we're going to get things like, and I'm sure you remember from electromagnetism, we're going to get things like Q is equal to the integral of d3x rho of x comma t, and we'll get a conserved current conservation equation. And if charge is flowing, we'll get dq dt is equal to minus, from the divergence theorem, Gauss's theorem, minus the integral. Oops. So I'm sure you're all familiar with this from electromagnetism. So for fields, our symmetry goes like this. We take a field and we translate it, or we transform it. And again, we define d phi a is equal to the partial of phi a with respect to lambda, evaluated at lambda equals 0. Now we have a little bit, because we're working locally, we define the infinitesimal symmetry. As dl is equal to the partial of mu of f mu. And again, this symmetry holds regardless of equations of motion. Okay. And paralleling our discussion of global charge, we define a current J mu is equal to pi mu a d phi a minus f mu. Now, remember from our previous lectures, or at least Coleman, pi mu a is defined as the partial of the Lagrangian with respect to the partial of mu of phi a. So this is all in relativistic notation. So for mu equals 0, that would be just the canonical momentum. And now Noether's theorem implies the infinitesimal symmetry is a conserved current. What do we mean by that? We mean that the forward divergence vanishes. So the partial of mu, of J mu, has to equal 0. Now from our definition above here, let's calculate it. So this is equal to partial of mu pi mu a d phi a plus pi mu a partial of mu d phi a minus the partial of mu f mu. And now this is equal to the partial of L with respect to phi a that's from the equations of motion d phi a plus putting in our definition here Now, this part, you can easily see that the first two parts here is just the change in the Lagrangian. The Lagrangian depends on phi and the partial of u phi a. So just using the chain rule, this is going to be the change in the Lagrangian minus the partial mu of f mu, which is equal to 0 because of the way we defined dl. So that's again like a two-line proof of Noether's theorem. And here we define the charge Q as the spatial integral of the time component of the current, which is equal to pi 0a d phi a minus the integral of d3x f0, which is equal to I'll rewrite it. And here I've just defined f again as in the field theory case, the spatial integral of the time component of f0. So, so you see the analogy of what we did before. Okay, now it's important to note that conserved currents are not uniquely defined. Some of you may know this, because let's just write down our basic equations. This is the basic equations for turn to crank. In classical, I'll call it classical field theory. And we can always add, to show it's not unique, we can always add a divergence of an anti-symmetric tensor to J mu, and not change the divergence of J mu. I mean, this is easy to see. J mu goes to J mu plus the partial nu of A mu nu. A mu nu equals minus A nu u. Then the partial of mu of J mu goes to the partial of mu of J mu plus the partial of mu partial nu A mu A nu, and this vanishes because A is anti-symmetric and two partial derivatives like that are symmetric. So we still get the partial of mu of J mu, which still equals 0. So we have many possibilities for the currents, and Coleman says this is a good thing, so we can find something that we like. And indeed, as we'll see in a little while, many times we get currents that don't have, like the stress energy tensor, that don't have the properties that we want, like symmetry and various other properties. So there's a lot of different, in the literature and in physics textbooks, there's a lot of different currents, especially for more advanced theories. For elementary theories, the currents usually given by the canonical procedure that we'll describe usually work well anyway. So, by the way, the charge Q also remains unchanged because Q is equal to the integral of d3x j0 goes to the integral of d3x j0 plus the partial of I a0i. And this is, by the divergence theorem, this becomes a boundary term. Boundary term at infinity. And we assume that all fields vanish at spatial infinity. Okay. Now let's handle the case of space-time translations. So as before in the mechanics case, we have VAX, field goes to and E is a constant 4 vector. I'll denote it by E rho. We're using covariant notation now. So now again, d phi A, which is equal to our usual definition, just ends up being E rho times the partial of rho VAX. Now, for those of you who are just starting their studies of quantum field theory, what you'll see in the coming up right now is a lot of quantum field theory, at least initially, is just index manipulation, and you really have to get used to seeing upstairs, downstairs, metric, and otherwise tensors. So don't let that scare you. But there's no other way to, no other language for us to use unless we use some kind of abstract mathematical notation where you won't understand anything anyway. So we're assuming everything is translationally invariant. Let's go calculate dl. The partial of L with respect to phi A, d phi A, plus the partial of L with respect to the partial of nu of phi A, times the partial of nu d phi A. In other words, we're assuming that our Lagrangian doesn't depend on coordinates, because then it can't be translationally invariant. So this is equal to E rho. I'm just going to factor out the E rho part, at least for now. Remember, E is a constant, so we can do that legitimately. And we can write this as just epsilon E. I'm changing notation. E rho times the partial of rho of L. Because again, this is the chain rule. And this can also be written as the partial of mu G mu rho E rho L. And you can see that because this will raise the, this will make this be an upstairs partial derivative with respect to rho. And so this defines, remember, we wanted to get our dl as equal to the partial of f mu with respect to, let me go back and see where I defined partial, I'm sorry. So this thing over here is now our f mu. So let's just keep that in mind. Okay. And our conserved current, from our usual definition, now what we do here is, as we saw before, there's only a certain number of independent parameters, so we factor out the E and we define a canonical energy momentum tensor. And we define it as T rho mu is equal to pi mu A and since we established before Noether's theorem, we know that this will satisfy, because again E is constant, so we can factor it out. Those of you who have studied general relativity are familiar with these equations, except here the T is not symmetric. Not symmetric. It will be for a lot of our simple theories, like a simple Klein-Gordon scalar field, it will be symmetric. But in general, it's not symmetric. And you can see just by looking at it, this part is symmetric, but this one isn't. Switching these two indices ruins it. I also want to show you on the T the mu index comes from the J mu, and it corresponds to density for a time index, and a current. Remember, for like think electromagnetism, the zero component is the charge density rho, so that's a density, and the I components is the current flow of current, current density, current for a spatial index such as I. Now the rho index this thing tells you what index mu applies to. We said already that it's either a density or a current, but of what? So if rho is 0, then it's energy. This is why we call it the energy momentum tensor. The first component on it describes energy, so we'll end up getting like energy, either energy density or energy flow. And then for a spatial index, it will be momentum. Okay. As I said, the canonical tensor is it's not unique. Let me not use that. That looks too much like electromagnetism. Is not unique, and in general not symmetric. And just to give you an example, if we were to compute, let's say, t0, 0, we would get pi 0a, partial 0, phi a, minus g0, 0l, which is equal to pi a. Remember, the zeroth component of this object is just the canonical momentum. Phi dot a minus l, which is our definition of the Hamiltonian density, so we end up getting energy density, as we expect. Okay. Now let's go to Lorenz transformations. Remember, we're doing space-time transformations, and that's covered by the Poincare group, which involves translations, 4 translations, space and time, and 6 Lorenz transformations, 3 rotations and 3 boosts. So it's a little bit harder to do the Lorenz transformations. And this will end up leading to angular momentum conservation and motion of the center of mass. Motion of center of energy. When we treat things relativistically, we don't calculate the center of mass, we calculate the center of energy. So here we have x mu goes to x mu plus epsilon mu nu x nu d lambda. Epsilon mu nu is equal to minus epsilon nu mu. It's anti-symmetric. 6 parameters. And if equations like this you're not familiar with, this is an infinitesimal Lorentz transformation. I would suggest you review some of the earlier lessons in this course. So we expect to get expressions like J mu is equal to 1/2 In other words, it's always going to be linear in the parameters. Now we're going to have a 3-component object because we're doing rotations. That adds another component. And then we would expect that we factored out the epsilons, and then the partial of mu, j mu, conservation. If this equals 0, it implies that the partial of mu of m lambda rho mu equals 0, because again the epsilons are constant. Obviously, a lot of books will have the mu index as the first index instead of the last index here. This just depends on what notation you decide to use. So we should get, since we have 6 parameters, we should get, as I said, 6 global conservation laws. And These will be given by like j lambda rho is equal to the integral of the time component. And 3 of these will give angular momentum conservation, and 3 will give the steady motion of the center of mass. So let's do the calculation for scalar fields. So we're not no spin. So if we get an angular momentum, we expect it will only be orbital angular momentum because we're not doing spin. So now, if you recall from our lessons on Lorentz transformations, Vax goes to Va lambda inverse x. Lambda is the Lorentz transformation. And we're going to do only infinitesimal ones. So we'll get x rho minus epsilon rho sigma. Here I'm just making use of the anti-symmetry to get rid of that minus sign. Let me look at this for a second. Offhand, this doesn't seem right. Taylor expanding here. So I have Va x rho. I should take the partial of Va with respect to x rho. Epsilon sigma rho x sigma d lambda. Let me check that equation. Bear with me a second. Okay, yeah, it's partial Va. This thing has a rho component here, so it's just we take the derivative of Va with respect to x rho, and then we multiply it by the whole thing, which is the rho component. So that's correct, I hope. So this implies that using our usual notation, now I'm going to lower some indices and raise some others. Okay, I think I'll probably need that a few times. And we also have that the Lagrangian, we always assume the Lagrangian is also a Lorentz scalar. You know, it's built out of scalar fields, but it itself is also a scalar. So we can think of phi A as being just L. And we get dl is the partial of mu. I'm sorry. I'm skipping a step here. This video is going to run kind of long, and we're near the end, but I appreciate feedback. If you want me to break these up into shorter videos, I can always do that. And we can rewrite this because epsilon is a constant as So, and now I can rewrite this even more, doing some index gymnastics. As the partial of mu, I can introduce mu and then raise it immediately. And again, this is defined as the partial mu of f mu. So this defines inside here, defines our f mu. Okay, so the conserved current J mu is equal to pi mu A d phi A minus f e mu. Here's where the turning the crank comes in useful, because you don't have to, you just got to plug into all the previous general formulas we defined and everything will work out. Oops. So here we just substituted, and I factored out those parts. So if you remember our definition of the canonical energy momentum tensor earlier, this thing is just but we would prefer to write it a different way, because the symmetric part is usually irrelevant. If T was symmetric, no, I'm sorry. Because epsilon is anti-symmetric here, the symmetric part of this object, whatever it is irrelevant. So we should anti-symmetrize this object. So that leads us to J mu is equal to 1/2 epsilon sigma rho x sigma t rho mu. Remember, we're going to anti-symmetrize on the sigma and rho indices, minus x rho t sigma mu. And this is our object, J mu. And based on what we wrote before, that implies when we factor out the parameters, that's another nice looking expression. And so M, it's a 3-index tensor, but it's really a collection of 6 objects labeled by antisymmetric by the antisymmetric pair of indices sigma and rho, and each of which has 4 space-time components. Labeled by mu. So for example, if we were to calculate J12, the integral of d3x x1 t20 minus x2 t10. So this is the z component of angular momentum. Again, I should say orbital, because we're not treating any spin. Now, we're familiar with angular momentum being conserved, but let's write out ji0. This is equal to the integral of d3x x1 t00 minus x0 t10. This is equal to the integral of d3x x1 t00 minus tp1. x0 is time, and since we're integrating over space, that comes out. And the integral of t10 is just the x component of momentum. So what this is saying is that when we take the derivative of this, we'll make it 1. You know, I meant to just treat the 1 case. This is equal to 0, and this says basically d dt, the integral of d3x x1 t00 minus p1. So basically what it's saying is that the change in the in this quantity, which you should recognize this quantity is just the x1 component of the center of energy. So it's just the T00 is the energy density, so we're sort of taking like the mass times x. And then what we're saying is that the rate of change of the center of mass or the center of energy, how it's moving, is constant. It's just the x component of momentum. So it all works out, and as I said, this is a fairly long video, but what we haven't covered is we haven't covered internal symmetries. And so the next videos will go on to internal symmetries, and we'll find some very interesting symmetries relating phase and charge, and we'll get to the non-abelian symmetries. Thank you very much for watching. I'll see you next time.